To determine the correct size inverse time circuit breaker for a feeder supplying multiple motors on a 480-volt three-phase delta system, we need to follow a step-by-step calculation process according to the National Electrical Code. Let's consider an example where we have one 15-horsepower motor, two 10-horsepower motors, and one 75-horsepower motor with a 15-minute intermittent duty cycle. Firstly, calculate the full load amperage or FLA of each motor. For a 15-horsepower motor operating at 480 volts, the FLA is approximately 21 amps. For a 10-horsepower motor operating at 480 volts, the FLA is approximately 14 amps. And for a 75-horsepower motor operating at 480 volts, the FLA is approximately 96 amps. These FLA values can be found in NEC Table 430.250. Secondly, adjust the FLA for the intermittent duty cycle of the 75-horsepower motor. According to NEC Section 430.22 E, for intermittent duty motors, we can apply a duty cycle correction factor. In this case, the motor operates on a 15-minute intermittent duty cycle, which corresponds to a duty cycle factor of 85%, or 0.85. Therefore, the adjusted FLA for the 75-horsepower motor is 96 amps multiplied by 0.85, which equals 81.6 amps. Thirdly, calculate the total FLA of all motors. This is the sum of the FLA of each motor, including the adjusted FLA for the intermittent duty motor. The total FLA is 21 amps for the 15-horsepower motor, plus 14 amps for the first 10-horsepower motor, plus 14 amps for the second 10-horsepower motor, plus 81.6 amps for the 75-horsepower motor. This gives us a total FLA of 130.6 amps. Fourthly, determine the overcurrent protection required for the feeder. According to NEC Section 430.52, for inverse time circuit breakers on a delta system, the recommended multiplier is 2.5. This multiplier is used to determine the maximum allowable overcurrent protection for the motor feeder. Therefore, the overcurrent protection is calculated as the total FLA multiplied by the multiplier. In this case, it is 130.6 amps multiplied by 2.5, which equals 326.5 amps. Fifthly, select the appropriate breaker size. The calculated overcurrent protection value is 326.5 amps. According to NEC Section 240.6, we need to select the next standard breaker size above this value. The nearest standard breaker size above 326.5 amps is 350 amps. Therefore, the correct breaker size for this feeder is 350 amps. It is important to note that the duty cycle factor reduces the allowable FLA for motors that operate intermittently. This helps to prevent nuisance tripping of the circuit breaker due to temporary overload conditions. Additionally, the overcurrent protection multiplier ensures that the breaker trips before the conductors overheat, protecting the motor and the electrical system from damage. It is always recommended to choose the next larger standard breaker size to provide adequate protection. However, it is also important to ensure that the breaker size does not exceed the ampacity of the feeder conductors. If the calculated breaker size is larger than the conductor ampacity, we would need to increase the conductor size or reduce the breaker size to comply with the NEC requirements. Let's delve deeper into the NEC sections referenced in this calculation to understand the reasoning and requirements behind each step. NEC Section 430.22 E pertains to the conductors supplying several motors or a motor and other loads. It specifies the ampacity of conductors supplying two or more motors shall not be less than 125% of the full load current rating of the highest rated motor, plus the sum of the full load current ratings of all other motors in the group. In our example, the 75 horsepower motor is the highest rated motor, so we would start with 125% of its FLA. However, since the 75 horsepower motor has an intermittent duty cycle, we can apply the adjustment factor from NEC Table 430.22 A. This table provides the percentage of motor nameplate current rating for various types of duty. For 15-minute rated motor, the percentage is 85%. Therefore, instead of using 125% of the 96 amps FLA of the 75 horsepower motor, we use 85% of 96 amps, which is 81.6 amps. Next, we add the FLA of the other motors, 21 amps for the 15 horsepower motor and 14 amps for each of the 10 horsepower motors, resulting in a total conductor ampacity of 81.6 amps plus 21 amps plus 14 amps plus 14 amps, which equals 130.6 amps. This is the minimum required ampacity for the feeder conductors. NEC section 430.52 provides the requirements for motor branch circuit short circuit and ground fault protection. This section specifies the maximum rating or setting of the motor branch circuit short circuit and ground fault protective device. The type of protective device allowed includes inverse time circuit breakers, instantaneous trip circuit breakers, and fuses. For inverse time circuit breakers, which are commonly used, the maximum rating or setting shall not exceed the percentages of the motor full load current as specified in Table 430.52. Table 430.52 lists the maximum percentage of motor full load current for different types of motors and protective devices. For inverse time circuit breakers, the percentage is typically 250% for motors with a full load current of 100 amps or less, and 225% for motors with a full load current greater than 100 amps. In our example, the 75 horsepower motor has an FLA of 96 amps, which is less than 100 amps. Therefore, we can use the 250% multiplier. However, this multiplier applies to the individual motor branch circuit protection, not the feeder protection. For the feeder protection, we need to consider the total FLA of all motors connected to the feeder. As we calculated earlier, the total FLA is 130.6 amps. Applying the 250% multiplier to the total FLA, we get 130.6 amps multiplied by 2.5, which equals 326.5 amps. This is the maximum allowable rating for the feeder overcurrent protection device. NEC section 240.6 specifies the standard ampere ratings for fuses and inverse time circuit breakers. This section lists the available standard ratings for overcurrent protection devices, such as 15 amps, 20 amps, 25 amps, 30 amps, 35 amps, 40 amps, 45 amps, 50 amps, 60 amps, 70 amps, 80 amps, 90 amps, 100 amps, 110 amps, 125 amps, 150 amps, 175 amps, 200 amps, 225 amps, 250 amps, 300 amps, 350 amps, 400 amps, 450 amps, 500 amps, 600 amps, 700 amps, 800 amps, 1000 amps, 1200 amps, 1600 amps, 2000 amps, 2500 amps, 3000 amps, 4000 amps, 5000 amps, and 6000 amps. When selecting the overcurrent protection device, we must choose the standard rating that is closest to, but not higher than, the calculated value. In our example, the calculated maximum allowable rating for the feeder overcurrent protection device is 326.5 amps. The nearest standard rating below this value is 300 amps, and the nearest standard rating above this value is 350 amps. According to NEC section 430.52, C1, if the calculated value does not correspond to a standard rating, the next higher standard rating shall be permitted. Therefore, we can use a 350 amp circuit breaker for the feeder protection. However, we must also ensure that the feeder conductors are adequately sized for the 350 amp overcurrent protection. The ampacity of the feeder conductors must be equal to or greater than the rating of the overcurrent protection device. If the feeder conductors are not adequately sized, we would need to increase the conductor size or reduce the breaker size to comply with the NEC requirements. In summary, to determine the correct size and burst time circuit breaker for a feeder supplying multiple motors, we need to calculate the full load amperage of each motor, adjust the FLA for any intermittent duty cycles, calculate the total FLA of all motors, determine the overcurrent protection required for the feeder based on NEC section 430.52, and select the appropriate breaker size based on NEC section 240.6, ensuring that the breaker size does not exceed the ampacity of the feeder conductors. By following these steps, we can ensure that the motor feeder is properly protected against overcurrent and short circuit conditions, while also complying with the requirements of the National Electrical Code. Remember to always consult the latest edition of the NEC and consult with a qualified electrical professional for specific applications and interpretations of the code. It is important to understand the specific requirements and limitations of the NEC in order to ensure the safety and reliability of the electrical system. In addition to the steps outlined above, there are a few other considerations that may be relevant when sizing the overcurrent protection for a motor feeder. One consideration is the coordination of overcurrent protection devices. It is important to ensure that the overcurrent protection devices in the system are coordinated so that a fault or overload condition will be cleared by the device closest to the fault, minimizing the impact on the rest of the system. This can be achieved by selecting overcurrent protection devices with appropriate time current characteristics and by coordinating the settings of the devices. Another consideration is the voltage drop in the feeder conductors. Excessive voltage drop can cause motors to operate inefficiently or even stall, and it can also damage sensitive electronic equipment. To minimize voltage drop, it is important to select conductors with adequate ampacity and to keep the length of the feeder conductors as short as possible. The NEC provides guidelines for calculating voltage drop in conductors, and it is important to follow these guidelines when designing a motor feeder system. Finally, it is important to consider the environmental conditions in which the motor feeder system will be operating. Factors such as ambient temperature, humidity, and the presence of corrosive substances can affect the performance and lifespan of electrical equipment. It is important to select equipment that is suitable for the specific environmental conditions in which it will be used, and to take appropriate measures to protect the equipment from damage. This may include using weatherproof enclosures, corrosion-resistant materials, and temperature-compensating devices. In conclusion, sizing the overcurrent protection for a motor feeder is a complex process that requires careful consideration of several factors, including the full load amperage of the motors, the duty cycle of the motors, the type of overcurrent protection device, the ampacity of the feeder conductors, the coordination of overcurrent protection devices, the voltage drop in the feeder conductors, and the environmental conditions in which the system will be operating. By following the steps outlined above and consulting with a qualified electrical professional, we can ensure that the motor feeder system is properly protected and that it operates safely and reliably. The National Electrical Code is a comprehensive set of standards and guidelines for electrical installations, and it is essential for electrical professionals to be familiar with the NEC and to follow its requirements when designing and installing electrical systems. The NEC is updated every 3 years to reflect the latest advances in technology and to address emerging safety concerns. It is important to stay current with the latest edition of the NEC and to understand its requirements in order to ensure the safety and reliability of electrical systems. In addition to the NEC, there may be other local codes and regulations that apply to electrical installations. It is important to check with the local authorities to determine the specific requirements in your area and to comply with all applicable codes and regulations. Electrical work can be dangerous, and it is essential to take appropriate safety precautions when working with electricity. This includes wearing appropriate personal protective equipment, such as safety glasses, gloves, and insulated footwear, and following safe work practices such as de-energizing circuits before working on them and using lockout-tagout procedures to prevent accidental energization. It is also important to be aware of the potential hazards of electricity such as electric shock, arc flash, and arc blast, and to take steps to mitigate these hazards. Only qualified and experienced electrical professionals should perform electrical work. If you are not qualified to perform electrical work, it is important to hire a licensed electrician to do the work for you. A licensed electrician has the knowledge, skills, and experience to perform electrical work safely and in compliance with all applicable codes and regulations. Hiring a licensed electrician can help to ensure the safety and reliability of your electrical system and to protect your property and your family from harm.